Hello. This is a lesson about the causes of constant velocity motion and constant acceleration motion. We've studied both extensively, but we haven't spent a lot of time talking about why things happen like they do. This video is a recap of a class I taught via Zoom during the COVID crisis of 2020. Hopefully it will be a useful review for people that year and future students who are struggling with why do objects act the way they do. We use this worksheet as a guiding example of what's going on. So let me throw that up here. The first thing I did is I asked students to take a minute and answer a couple questions. So I asked them to sketch the three important motion graphs, position, velocity, and acceleration, for an object moving with constant velocity. I then asked them to think about all the motions they've seen so far where an object moves at constant velocity. And I asked them to answer for me what they think causes constant velocity motion. So we spent some time in Zoom breakout rooms discussing that. And the answers we came up with were that if you have a constant velocity, that means the slope, the velocity on your position time graph is constant. On a velocity time graph, you have one velocity that never changes. And since that velocity is not changing and the slope on this graph is 0, it means you have no acceleration. So I think back to the motions we've done so far with constant velocity, and I feel like it's a little misleading, the ones we've picked, if we're trying to think of what causes this. So the motions I could think of that we came up with for constant velocity were basically walking at constant speed and driving at constant speed. And that sort of sends the message that to go constant speed, you need some sort of force from your feet or from an engine. Let's watch one more motion. What I've got here is a motion detector. And a motion detector, it actually works the same way a bat, the little furry flying mammal, goes hunting. A bat uses something called echolocation, which means it sends out a click of sound. That sound goes off, it bounces off its target, it bounces back. And the bat's brain can actually process the difference in time between when it clicked and when it heard its click. And that lets it make a map of where bugs are and things like that. So this thing does something similar. There's a sensor here that makes a click, and it sends the clicks out, and it's going to reflect off this stack of textbooks I got here. And those clicks are going to bounce back and be detected by the computer. So I'm just going to go over here to start. Give it a push. And now stop. So we have this graph here. Since this is a position time graph, we can see that there's horizontal, slope of 0. That's when the cart was not moving. We then have a positive slope that's relatively constant. It was going in this direction. And then, after I stopped it, back to a slope of 0. That's when it was stopped down there. The reason I wanted you to see that particular motion was, unlike our other constant velocity motions, there was nothing keeping that cart going. In the other labs, we had someone walking and their muscles were pushing, or there was a motorized vehicle, but here it just coasted. And you saw from the graph that was plotted on the screen, it appeared to be constant velocity. It appeared to be a straight line. Now we know that that wouldn't have gone on forever. We know it would have slowed down. But a guy named Galileo Galilei in the 1500s, he realized that the only reason it would slow down was because there was something messing with that cart. There was something pushing on it. And pushes or pulls are the next topic we're going to have to discover if we want to understand how motion changes. Galileo began to formulate what we now call Newton's first law. Objects in motion stay in motion unless acted on by a force. Objects at rest stay at rest unless acted on by a force. There's a certain parallelness to those two statements, So you can kind of combine these two and say objects keep doing what they're doing unless you force them to do otherwise. This video is to discuss how Newton's first law was discovered. And the strange thing is, although we call it Newton's first law, the research was done by Galileo nearly 100 years earlier. And what Galileo was interested in was how objects roll up ramps. So he had an experimental setup, kind of like I have here. I have a ramp. I'm going to drop these two brass cylinders down it. They're going to roll up these two other ramps. And one of them is short and steep. The other one is long and shallow. The reason Galileo was looking at different ramps was by changing the steepness, he was actually changing how much of the force of gravity was acting on the motion. The more horizontal, back, forth the motion is, the less the force of gravity is going to have an effect on it, because gravity is an up-down vertical force. So by making the ramp short and steep, you had more of the gravity force acting. By making it long and shallow, it's kind of like you diluted gravity. Galileo in the 1500s didn't have the ability to go to space or anything, so this was the only way he could really increase or decrease the effect of gravity. So what we'll do, you'll see this from a couple different angles. You'll see these two cylinders roll up, one from the perspective you have now, and once from a camera that's over here. And then after this whole video is over, you'll see a screenshot from Tracker, so you can see precisely where the two stopped. So let's do the experiment. So I plugged that video into Tracker, and you can see the results. Regardless of whether you were on the steep ramp or the shallow ramp, the tracks end at the same height. The two cylinders went to the same height. Galileo got to thinking, and he realized that as he was diluting gravity by making the ramp shallower and shallower and shallower, eventually the shallowest he could get would have the object rolling for a very, very long time before it ever got to that final height where it has to stop. And what if he went to the extreme and he had a perfectly flat ramp? Well, then gravity would be diluted basically to zero. And what would you expect the object to do? Well, it would just be an object in motion. And he realized that without any other forces, it should just stay in motion. So Newton's first law, objects in motion stay in motion unless acted on by a force. Objects at rest stay at rest unless acted on by a force. So what is the cause of constant velocity motion? It's not a force. In fact, a force would be the only thing that could disrupt constant velocity motion. Constant velocity motion seems to just happen. It happens naturally. So in order to kind of hint at why that might be, I showed a clip from the 1960 classic Frames of Reference. And all classes have watched this. If you have not, I highly recommend it, and I will have links for you. But we watched Drs. Ivy and Hume drop a ball on a cart that could move at constant speed. We watched it from various perspectives. We watched it sometimes moving with the cart, sometimes not moving with the cart. And what we found out really quickly was that the difference between being at rest and being at constant speed was sort of a matter of our perspective. That in reality, there didn't seem to be a big difference between those two things. That it's usually written objects in motion stay in motion, objects at rest stay at rest, unless you have a force. And from everything we just learned about from frames of reference, that there's not really a difference between in motion and at rest, a better way to say that is that objects keep doing what they're doing unless acted on by a force. You could also put that as objects are lazy. And just to make it sound more sciencey, we'll use Greek. Objects have inertia, which means laziness. And they don't want to change what they're doing unless you force them to do it. So what we need to do now is we need to look at what happens when we put forces on different objects. So I put students into breakout rooms again, and I asked them to sketch the graphs for constant acceleration motion, because that's the kind of motion we'll have when there are forces. And this is what they came up with. It didn't have to be these parabolas. Depending on what direction the force was, the acceleration could be positive or negative. The initial velocity was kind of up to how the object started, so this graph could have very different VOs, and our parabolas could all be different. But at the end of the day, we have a parabola for position, a line for velocity, and a horizontal line for acceleration in a constant acceleration situation. And the examples we've seen so far in class of this are a car speeding up, something falling in a gravity field, pulling someone with a constant force, and the common factor here is forces. To cause acceleration, you need forces, and that's kind of where we're going in this unit. We have to learn about forces. So a force is a push or a pull, and there's a lot of forces. These are ones that one of my classes came up with via Zoom. Here's some other ones that another class came up with a few years back. So usually we show forces on objects by drawing arrows in the direction of force. That's something called a free body diagram. And basically, gravity pulls you towards a planet. It's actually more complicated than that, but for now it's good enough. Friction is something that resists motion. If a box was trying to slide this way, friction would pull it back. Normal forces are the forces you feel when you try to sit in a chair or walk into a wall or stand on the ground. They're the forces a surface puts on you to stop you from being able to move into the surface. I know in chemistry and earlier classes you've learned about how positives are attracted to negatives, and negatives repel each other, positives repel each other. Those are called electrostatic forces. We've talked about air resistance, how moving through the air puts a force on you, sometimes called a drag force or an air resistance force. And then just generally any push or a pull can be described as a force. We typically call a pull through a rope a tension. So the best way to describe Newton's first law, that objects don't change what they're up to unless you force them, is to do one of my least favorite demos of all time, the old tablecloth and dishes trick. I'm always afraid I'm going to break my face doing this, or at least some dishes. And here's a nice example from 2019 where I did not, in fact, break anything. Because in Newton's first law, the cup and plate are objects at rest, and they want to stay at rest. So if I get the tablecloth out from under there before it puts too much force on them, they should stay in place. All right, survived. So if you get a chance, this is a more fun demonstration of the law of inertia, that you need a force to cause an acceleration, and in its absence, objects won't accelerate. This was on The Tonight Show about 45 years ago. And Johnny Carson, this gentleman here, was the host. This is Dom DeLuise, who is a famous actor, and we still watch some animated movies with his voiceovers in it. But they do a great version of this trick here, and I hope you guys enjoy it. I'll have a link up on my classroom as well. But the key thing in both those cases is without a force, the objects didn't accelerate. But there's a little more to the story than that, because you probably noticed that my tablecloth and dishes did accelerate a little bit, just a tiny bit. And you might also have been wondering why I chose to use heavy pieces of glass and breakable ceramic plates. Don't worry too much, they're from Dollar Tree, so when I break them I won't be too sad. But I can't do this with unbreakable plastic plates. And the reason is, every time I try to, even the little force that the tablecloth puts on them sets them flying fast. I need big, massive things in order for the tablecloth coming out from under not to set them in motion. So clearly, the object itself affects how forces change its motion. And clearly, how massive the object is something that's important. So it's time we look at a few other definitions. So mass is something you studied in other classes, and usually we think of it as the amount of material we have. We put chemicals on a balance and weigh out how much mass out how much material there is. But it turns out that mass is actually also a description of how much an object resists changes in motion. So I give it that same Greek word, inertia, laziness, to describe mass. And the more inertia, the more mass something has, the harder it's going to be to get it to accelerate. Let's take a look at a lab where we investigate this pattern. We have previously said that mass is the same as inertia, or laziness, how hard it is to get an object to change its motion. In this lab, I'm hoping you'll get a feel for that. You're going to have a variety of masses and a hanging spring. We put a mass, say a 100-gram mass on a spring, give it a gentle little tug. It bobs up and down with a certain period, a certain amount of time it takes to go back and forth. Check out what happens if I make the mass larger. We'll say 500 grams. Give it the same tug. It takes a lot longer. The 500 grams is lazy. It's harder to change its motion. And it takes the spring longer to do it. So in this lab, we're going to try a big variety of combinations. And we're going to time how long it takes for a complete back and forth, which is called a period. We're going to see if there's a relationship between period and the amount of mass that we're putting on it. For some masses, like this 50 gram, it's going to be going so fast that it would be hard to start and stop our stopwatch for a single up and down. So one trick that has worked for a lot of people over the years is to count 10 up and downs and time that, and then we can divide whatever time we have by 10, and then we get a more accurate answer. We average our error out across more observations. In order to time, get your weights going up and down evenly. You don't want them jerking violently. Grab a stopwatch. You can use your phone if you want. And what you're going to do is when the weight gets to the very bottom, say 0. And then each time it gets to the bottom again, count up until you get to 10. For the faster ones, you're going to want to do this in your head because you won't have time to say it. But you're going to start the watch on 0 and stop it on 10. So you're going to get the value for 10 up and downs. So here we go. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 5.93, and that is 300 grams going up and down. So for 10 periods for 300 grams, I'm going to put 5.93. I don't have every value between 50 and 1,000 here. I just have the ones I can make with this set of weights that I got. But I'm going to go through and get all this data now, and then we'll graph it. So here is 50 grams. Here's 150 grams. Here is 250 grams. Here's 350 grams. Here's 600 grams. And here's 1,000 grams, or 1 kilogram. So here's our data. So we're just going to divide by 10 to get all of these. So that's pretty simple. You just have to move the decimal place 1 to the left. So this would be 1.086, 1.014, etc. 0.987. So I think you already saw the pattern. As the mass gets larger, so does the period. It's a positive correlation. So what's going on is basically that the spring is trying to change the direction of the weight. And the more mass it has, the more inertia, the harder it is to do. So something that's not very lazy without much inertia, it's easy to change. something that's got a lot of inertia, it's hard to change it. That's why we see the longer period. You can actually use this as a type of scale, almost, to measure someone's mass in situations where regular scales don't work. Let's talk about that. Gravity, the force of gravity in everyday life is usually called weight. So what I want to do before we even get into other pushes or pulls, I want to make sure we understand the difference between the force of gravity, which is how hard the Earth is pulling us, and another related concept called mass. These things together are going to make up the bulk of this unit. So here's a couple more definitions. Weight, the force of gravity, is literally how hard the Earth is pulling on you. In order to demonstrate what mass is, I've got this device here called an inertial balance. And it's basically just a couple of pieces of metal held together by hacksaw blades. When I give it a push and let it go, it vibrates back and forth really, really quickly. And it does this, and the hacksaw blades are able to accomplish this because it's not very lazy. It doesn't have a lot of mass, and it's really easy to change its motion. So what I'm going to do is I'm going to put this C-clamp on it, which is going to give it more mass and more inertia, and we'll see what effect that has on its motion. Alright, so I've got the C-clamp on. That's increased its mass quite a bit. Check out what happens when I give this a push. It's a lot slower. And the reason is the C-clamp has added so much mass, and the C-clamp is so lazy, so much inertia, that it's a lot harder for the hacksaw blades to change its motion. NASA uses these inertial balances all the time to check the mass of astronauts when they're in orbit, where they can't be weighed because their weight appears to be zero. The Earth does not appear to be pulling them. So here's an astronaut, Commander Seddon, being massed back on the space shuttle. And they basically put you on one of those inertial balances and give you a push, and they measure the period of your motion, and they can convert that to a mass. There's literally a spring, and the more you pull on it, the more it pulls back on you. So it's actually not measuring the weight, it's measuring how much this spring is stretched. And it actually is getting the tension in that spring. And that's the number you're seeing displayed on that scale. A scale like this, or like the bathroom scale in back, that works a little bit differently. In that case, we are putting an upward force as well, but it's actually the force of the scale pushing upwards. It's not pulling up, it's pushing up. And that's called a normal force. The bottom line is, whether we're measuring mass or weight, in reality on Earth we're always measuring weight. The scales are always measuring how hard the Earth is pulling these objects. Because mass and weight are directly proportional on Earth, the force of gravity equals the mass times 9.8. You just have to change the numbers on the dial, whether you're going for mass or whether you're going for weight. So we'll look at these scales and we'll see that. The postal type scale, its dial is in pounds and ounces, and those are measures of weight. But you can see I've put conversion factors on there to turn them into mass. You just multiply by a number. That's even more obvious on the small spring scale. It's got grams and newtons. Grams is mass, newtons is weight. And you can see that there's just two different rulers, and you just read what the needle's pointing at for that scale. So there's another reason that sometimes people confuse mass and weight, and it has to do with the different measurement systems that we have. So I want to go to a grocery store, and I want to look at the scale we use for determining how many apples or peppers or potatoes you buy. We'll take a look at the units. So here's a bag of apples I bought, and as you can see, it's sold both in pounds for the US market in kilograms for the Canadian market. And that's a source of confusion because, as we've seen, pounds is a measure of weight, how hard the earth is pulling these apples, whereas kilograms is a measure of their inertia, how hard it is to change their motion. So I think you saw on there that there was pounds for measuring using US units, and kilograms for measuring using metric units. Problem is, those do not measure the same quantity. There's two other units we should learn. We should learn the metric SI unit that we're going to use in class for weight, or for all forces. It's called the Newton. And 1 Newton, or 1 pound, is 4.448 newtons. So a newton's about a quarter pound. In class, you'll see this little foam apple. Everyone can toss it around. It weighs a newton. Also, think of a quarter pounder with cheese. That's a newton. We'll use that all the time. There's another unit, obviously, the US unit for mass. There's a couple different ones you can put in here. One's called the slug. There's also the pound mass. You might run into those if you become an engineer. But bottom line is, we have one unit to distinguish inertia. We have another unit to distinguish the force of how hard something's pulling on you. It's important to keep them separate. All right, so I'm hoping from this lesson you learned a couple of key points. There is nothing that causes velocity. Velocity is completely dependent on the reference frame we're in as to whether something's moving or not. The law of inertia, Newton's first law, states that objects keep doing what they're doing unless you put a force on them. And if you put a force on them, that's when they start to accelerate or change their velocity. We also went through how mass affects how much a force can change an object's motion, that the more mass you have, the lazier you are, and the more you resist changes in motion. And we finished up trying to clarify the difference between mass and weight. Thanks for watching, and let me know if you have any questions.